for inviting me. I'm not a mathematician by any measure, so if I commit some heresy or sacrilege to mathematics, let's take it easy. Uh, so the results that Makesh showed you yesterday were from the earlier part of my PhD. I was very naive then. I did not know anything about MPI or parallel computing, so I developed my own version of MPI using Perl by exchanging tokens between processors. But I was after publishing the PNAS just in time, I was banned from my cluster. So they said, don't run this course ever again. And then I took courses on parallel computing and MPI, and these are the later part of the results of my PhD. So this work is done in so these two are my PhD advisors from University of Minnesota. And right now, after in 2019, I joined David Strolovic's group in Hong Kong as a postdoc. And after postdoc, I'm still continuing there as a research assistant professor. So what you see on the right is a potential energy surface. It's a graph of the potential energy surface. A graph as in a computer science graph, where there are edges and nodes. The nodes are nothing but energy minima, and the colors are the energy scale, and the red dots are the transition states, and the edges. What you cannot see is that the edges are endowed with additional properties, which are maybe the frequencies of minima or the transition states that are needed to compute the frequency factors for transition state theory, essentially the 1956 Vineyard equation. So, yeah, so I'll be applying this to nanosystems. So we'll be essentially concentrating in this region. Uh, the reason for that is nanosystems are very interesting because the thermal fluctuations should be dealt in on equal footing with the applied load. So for example, this is an experiment by Julia Greer's group at Caltech. They took a copper nanocolumn and they compressed it. So the blue ones are thicker column and the red ones are thinner column. And you see that the red ones, if the strain rate is very high, you see the average stress is very high. And if the strain rate is low, then the average stress is very low. But it is not so much in the thicker column, because in the thinner column, the system is essentially dislocation starved. So the surface actually plays an important role in nucleating the dislocations. And these jumps are nothing but strain bursts that you see. And we want to understand the rate dependence as well as the stochasticity. Stochasticity means that when you run the experiment multiple times, each time you see a different result. That is the essential objective of this work, and you want to create a predictive tool that uh, can take in all the complexity of the system and put it in a systematic way. So before we discuss about all the continuation stuff, let us spend a few slides on potential energy surface. I guess everyone knows by this time. So we have a set of atomic positions, and this is the internal potential energy. And then you can also have an external field, assume it to be conservative. Like you can apply a set of forces or external field, and the total force on each atom is a gradient of that. And typical methods, this is not an exhaustive list, but are molecular statics, where you have a system and you just quench it to a minima. That is a molecular statics. And then you solve Newton's equations with all the machinery of statistical mechanics to get thermodynamic properties. So that is molecular dynamics. And then you also sample the configurational space to get some idea of energies, and that would be eventually upgraded into thermodynamical properties through statistical mechanics. So that's the other way. Of course, there are other things like kinetic Monte Carlo, which I have not shown here. And the potential energy surface, you can think of it as each point on a potential energy surface is a particular realization of the system, and it is just a plot of this energy. And recall that forces are the gradients of the energy, and the equilibrium points are where these forces go to zero, that is the gradients vanish. So here we have a minimum. So that's an equilibrium point. The saddle, although it is not stable, that is also an equilibrium point, and the higher order saddle is also an equilibrium point. Uh, and the stability is given by the Hessian. So you take the second derivative and then try to see if it is positive or definite. And then you can define various paths on that. And one of the most useful pathway for doing thermodynamics is the gradient descent. You just go in the direction of the gradient that is determined by the potential of the surface. So essentially local minima or the metastable states, first order saddles or transition states in TST, and reaction path can be thought of as a motion on this energy landscape. Now, this potential energy surface is extremely non-convex. You see that there are multiple minima, many transition states, and many maxima. And from this paper in 1983 by Stillinger and Weber, they have given a kind of estimate of the number of structural minima in 1 gram of argon. You see 10 to the power of 10 to the power of 22. So it is extremely convex. So if you try to explore everything, it's actually infeasible and there is no point of doing that. Now, let us think about incremental loading or proportional loading where, for example, if you have a body, like what Patrick Farrell were talking about, they have a strut or something and they put load and that buckles. So that load itself or the strain itself is a loading parameter. So here we have a system and we incrementally compress it. So this is the increasing direction of the load, and let us call that compression lambda. That lambda can be anything. So now we introduce an additional parameter into your potential energy, that is epsilon of u colon lambda is this. The reason is that at each lambda you can have a different potential energy surface. As lambda keeps changing, the potential energy surface keeps evolving, and people usually use incremental loading simulations. Essentially, they increase the load a bit and then minimize, again load it a bit, minimize. And so that is how incremental loading algorithms work. But then again, the minima that you find is dependent on the algorithm that you use. Maybe steepest descent can give you a different minimum, or conjugate gradient can give you a different minima, and so on. So the algorithm itself is can introduce some kind of complications into this, and we don't want to get caught up in such inconsistencies. The problem that I'm going to solve for this presentation is I take a nickel nano slab. It is infinite in 1 dimensions and it has around 116 atoms and some of them are constrained. And the potential is EAM and it has certain symmetries. Yeah. So now if you take this column and you try to compress it, forget about the uh, dotted lines or dashed lines. You start with a perfect structure and you keep increasing the loading parameter lambda. And then these are von Mises strains. So I first computed the deformation gradient and from there the green Lagrange strain, and then I computed the von Mises strain to show the coloring. And you can see some kind of incipience of instability there. And what happens in reality is that it snaps through, it falls on one of the solution pathways. You never know what the solution pathway is, and then it goes on. So those are the strain bursts that we are talking about. What is the nature of this instability? So you have initially a stable well. As you keep changing lambda, that well becomes saddle and then the system rolls down. In a very general sense, think about that at each lambda you have a potential energy surface. You can parameterize lambda with time if you're talking about some kind of rate of loading. So the potential energy surface keeps morphing as the loading parameter progresses, and your dynamics will be happening on this evolving landscape. So this is like a driven system. The assumption is that we have assumed for this work adiabaticity in the sense that the boundary conditions do not alter the dynamics. So at each, the dynamics on the surface of the PES does not feel the change in boundary conditions. Just like what we do with Born-Oppenheimer approximation, we can also assume that. Uh, And you see that it is highly non-convex and there are multiple competing pathways. How do we model this numerically and then get some statistics out of this? So this involves systematically mapping equilibrium pathways, that is the solution to the equilibrium equation, and then explore the transition pathways on each slice of this bifurcation diagram. So each potential energy can be a slice that is running normal to the bifurcation diagram, and then propagate the system stochastically at a particular loading rate. Now, let me spend some time explaining what I think Mekaj and Patrick Farrell has already done this, but I'll spend a few minutes on this. So you have the energy, and then you have the equilibrium equations, and so this is not the potential energy surface. This is a series of potential energy surfaces. Actually, each one of these is a potential energy surface. Think like this is a buckling problem of a Euler beam or a 246 Ginsburg-Landau potential for first order phase transitions for austenite and martensite. So here you have a single stable state. And as you keep changing some parameter, maybe temperature or load in the case of buckling, two new minima keep emerging, and finally the centered state goes out of stability and the two ones survive. So this is your primary path. You keep increasing the load and you go to B and then you hit a bifurcation point, and then this one becomes unstable, so it's now dotted, and then two paths emerge out of it. They kind of turn this way, and then when this becomes stable, they are in thick lines, not dashed anymore. So this is actually uh, equilibrium path, and this is a bifurcation diagram. What essentially numerical continuation and branch following codes, the main ingredients are: we want to continue between critical points, identify, refine, and characterize the critical points. Use group theory because symmetry gives you more niceties for the equations. It sometimes lets you go to places where you cannot go without symmetry, and it also reduces the amount of computation. And you also should have a methodology of how to branch from a bifurcation from a critical point. So this, as I said, is already covered. So essentially, at the heart of this is the implicit function theorem. So if this is regular, then you can have a well-connected solution between 2 points. And we use numerical continuation to go from given C0, you can go to alpha 1 or alpha 0. Essentially, it is like you get a solution, you seek the next solution. And a good set of references are by H.B. Keller and Algover. For these more kind of algorithmic implementations of this. Uh, the next thing is, how do you parameterize this? One is natural parameterization. You can think of marching by slowly incrementing the lambda. So that is the most straightforward and the naive way of doing it. You keep increasing the load and then solving the system. This will work sometimes and then fails some other times. We'll see when. Or you can do some kind of Newton's method to solve this. But that fails when you have a critical point. So critical point is where there'll be a rank deficiency, and then you will see that bifurcations and folds happen at those points. In this case, it is like this is a bifurcation point. This is a turning point 1 and turning point 2. Of course, this is a symmetry variant of this one. So in order to follow through critical points, we use Keller's method of arc length continuation. So we have an additional equation to parameterize the arc length. And then we follow the solution, the equilibrium paths. And then you can use two variants of it. One is the regular one, which is pseudo arc length tangent approach, which is a regular approach. And you can also have an additional constraint that I want a solution within a ball of it. So this is a pseudo arc-length constraint approach. Why is this useful? Because sometimes, or most of the times, it is not enough to roughly identify the bifurcation point. We have to polish it to a very high degree of precision. Then we keep using a bisection method and keep forcing the solution point to refine the solution point. That is how we do this. And there are some issues. These are more implementational issues. So you need to have some kind of step length adaptation when you go through the critical points. And again, you need to be able to identify the critical points to see that some eigenvalues are going to through zero and negative. But if some things are like here, some things are going negative and some things are going positive, some eigenvalues, then you might see that, okay, this goes here, touches this point and comes back. You will miss that critical point. So you need some kind of preconditioning. So you also need those tools of that. Yeah, and then finally symmetry. This is a beautiful picture of an ancient Hindu temple from 1300. Uh, so what symmetry offers? Symmetry, if it is there in system, it will make itself evident by one way or the other, whether if you see it or not, it becomes so evident in the dynamics of it. So here is a simple truss. So this example is a kind of prototypical example for branch following and bifurcation, at least in the mechanical engineering field. So this is by Tim Healy from Cornell, I think so, yeah. So you have a truss dome. It has a hexagonal symmetry. And so the group is this one, and the generators are this and this. You can generate all the symmetries using this. And the energy is invariant under the symmetry operation. So you get this. So that means that the equilibrium equations show certain equivariance. And then so you can restrict the solution to a symmetry subspace and solve in that restricted space. That gives you two advantages. One is you can solve the system in a lower number of variables. I'll show that in the next one. And then it also allows you to capture bifurcation points, like pitchfork bifurcation points, or else you will miss them and misidentify them as turning points. So here is that. So if you do not use symmetry because of the numerical noise, you can actually completely miss that and go this way, and this is this way. Similarly, if it's a transcritical bifurcation, so you can go here and come back without even observing that. So symmetry allows you to capture that, and also you solve in a smaller space than the bigger space. U is the bigger space. You restrict it to a smaller space. So it gives you two advantages. Yeah. Now that we know what numerical continuation is and what potential energy surface is, let us try to do something with these tools. So we want to solve Julia Greer's problem of compression of nanocolumn. So as the load is increasing, the energy landscape is changing. So at a particular load, I want to know the potential energy surface. And as the load keeps changing, and I want to understand how this energy surface is lifted in the lambda space. So in chemistry terminology, we call it as the pathways on the potential energy surface. We call it as a kinetic transition network. So that encodes all the information of the barriers, maybe the frequencies at the minima and the saddle points. Saddle points are the most important ones statistically because the distribution is more concentrated in here and sometimes here. The transitions to the saddle point are fleeting. The system spends very limited time there. And this is the bifurcation diagram we have already introduced. So we want to do a marriage between these two. So we define certain things. Uh, we know what equilibrium points are, and we know what regular points are. Regular points are the solutions on the during the path following. And then we can segregate this regular points into different types. One is R0, which are the stable points, and R1 or the first order saddle points, and you can go to higher order saddle points, but those are from a statistical mechanics of point of view, they are not important. And you can also define critical points. Now, so the regular branches are nothing but a continuous connected set of these uh, uh, regular points punctuated by the critical points. So you can imagine the bifurcation diagram itself in a computer science sense as a graph. The edges or the equilibrium paths of different what do you say, whether it is stable, rank 1 or higher rank, and the nodes that are interleaved in this ones are the critical points where the paths bifurcate or the turn. So assume that this graph is going in the direction of lambda. So this is what essentially we defined, and for each path we can give each point on the path with a particular set of properties. And again, in computer science terminology, it is a weighted graph. So the edge has certain properties. Here, you can have all the frequencies, the energy barriers, onto the edges. Now, we have the bifurcation diagram. Now, we want to put it in relation to the kinetic transition network of each potential energy surface. So what we do is we construct a bifurcation diagram, and then if it is a saddle point, we spawn steepest descent in the two directions, the positive and negative directions of the tangent. And then we reach uh, two stable states. Everything happens in parallel. So think like a bifurcation diagram, a path in the bifurcation diagram is like a centipede, and these steepest descents are like legs. So these are eventually going to get latched on to the other aspects of the equilibrium map, and these things keep growing on as the code is run. Yeah. Uh, so now the uh, kinetic transition network becomes parameter dependent. So we call it a parameter dependent kinetic transition network. Now the equilibrium map is a combination of the bifurcation diagram and the PDKTN. So that is how we define that. Once we have that, we can do dynamics on an evolving system. Essentially, at each load, you know how the system, how the equilibrium points, or that is the minima, are connected to other minima through saddle points. And as you increase the load, how are these changing? How are these changing involves many aspects. One is the energy wells can become shallow, and when they become shallow, the curvature is going to change. So the frequency factors are going to change, and also the barriers are going to change, and the connectivities can itself change. So it is like a time dependent graph, but time is a lambda here. So now that we have equilibrium map, okay, this is some kind of troubles that I have gone through connecting by for making this equilibrium map work during my PhD. I had to, although this is embarrassingly parallel, it's not entirely embarrassingly parallel. The way it works is I start with an initial solution point, and the master node gives the solution point to a worker node. There are many workers. Each worker can be a single processor or multiple processors. And then it continues that pathway in, if a tangent is given, it continues in the direction of the tangent. If nothing is given, it can continue in both the directions. And until IFT fails, that is until it hits a critical point. And when the worker detects the two critical points, then it also computes the tangents that can come off that, out of that, and then it sends the data to the master. And then the master goes and like it's like a tube. It tries to fit everywhere with all the symmetries or these critical points already existing. with all the symmetry variants. And then if it fits, then it says, okay, throw it, and it gives a new job to it. If it doesn't, then it says, okay, this is a new path. Now it gives back the data to it. Then this centipede now grows legs. So the worker processor does steepest descent on each sides, and then it fills that. Then it goes to the master, and the master now sees that all the stable solutions that are coming from a saddle point, a saddle solution, and then it in the database it tries to locate where to latch onto, and then these things latch onto there, and finally you get this beautiful equilibrium map. The perpendicular direction is the bifurcation diagram, and the parallel direction is the PDKTN, and this one keeps evolving. Yeah, this is some algorithms that I want to skip. Now that we have this, let us do something useful for science. So we define three regimes. One is quench dynamics. Quench dynamics is the dissipation of the system is so high as if you are rolling down a hill that is coated with some kind of very high viscous fluid. So each time the kinetic energy that you gain because of loss of potential by losing down is immediately taken out of the system. You can actually do it in labs. So that is a quench dynamics. So the system can only roll down a hill, but it can never surmount a barrier. It doesn't have that energy. And the second one is a quasi-static path. So you give the system enough amount of time, like it's a thermodynamic limit. So the system at a particular loading lambda can explore the entire potential energy landscape. That is the extreme of that. And so it can go there, maybe it can find the most stable state out of the existing state, because we can never guarantee that we can find a global minimum. And finally, the most relevant one to experiments is driven dynamics, where lambda is changing at a particular rate. Of course, that rate is not so fast enough that it affects the dynamics on the evolving period. So adiabaticity should still be valid. So that is driven dynamics. The thing with driven dynamics is that the system is evolving, the dynamics is happening on an evolving potential energy surface. So the amount of exploration that the system can do is limited by lambda dot. That is the loading rate. Now we have these three regimes. Let us use the equilibrium map and connect and do the dynamics of this. Okay, now I show how this equilibrium map is built for this particular problem before I apply those three methods. So this is the first generation path. So this is the black one is the primary path, and then the red ones are the first generation ones. And I think there is some inconsistency. The not dashed ones are stable, and the dashed ones are unstable, and the dots are critical points. Now I do one more generation, and it becomes more complex. I do more, and it becomes more complex. Finally, I keep running. There are millions of bifurcation points and solution points in this. What you see here is uh, when I was presenting this to my PhD committee, most of it did not make sense to a lot of them. But anyway, now I think the people in this group will understand. So the blue ones are the stable. Sorry, the blue ones are the stable pathways, and the golden rod ones are the higher order saddles, and the red ones are the first order saddles. So from a physics point of view, only a statistical mechanics point of view, these two are important to us. But they are also important to us in the sense that they allow us to complete with the quotes, because you never have a complete bifurcation diagram. They are part of the game, but they directly do not enter into our thermodynamics. And yeah, I just replotted this. So this is the set of stable segments. I'll show the statistics at the end. And these are the first order saddles. And these are the higher order ones. Now, if you go to this one, if you slice it, that is a potential energy surface. So I sliced. So this is a simpler bifurcation diagram because I want to show some finite number of states so that I can plot the pictures. And the color codes of the atoms or local strains. So you can see that when you slice the equilibrium solution, these are all the stable states or many stable states at that particular lambda. Now, now that we have this for the nickel nanocolumn, we do the quasi-static part. It's essentially we minimize the energy. So that is how we construct the quasi-static path. And then the construction of quench dynamics is uh, you keep loading the system. So the potential energy landscape evolves, and then you hit an instability, and then you roll a dice and then roll down. Again, increase the load, roll a dice and go down, and so on, so forth. So that is how the quench dynamics works. And so this is the quench dynamics path that is on the lambda versus the potential energy. And this is how it looks when you plot it on the bifurcation diagram. And these are some of the structures that are along the quench dynamics path. Similarly, for the quasi-static path, we wanted to have, of all the available solutions, we want to look for the minimum. So we want to construct a lower envelope. So we take the equilibrium map, put it in like instead of plotting lambda versus the applied or the force or the stress, you plot lambda versus the potential energy. And so you construct a lower envelope of all the paths. So that is in the infinite amount of the time, the system can get sense of what is the minimum and can eventually go there. That is one kind of regime of dynamics. And this is in the lambda versus low stress space. Oh, and these are some of the states. You can see that uh, there are several defects in the system. So essentially, all the equilibrium paths are defected solutions. Now, let us try to compare these two to the experiments. So we'll be concentrating on the red ones because we are dealing with a nano column. And so the quasi-static path is extremely slow, and qualitatively here the stress strain path, the average stress is very small. And here you see the same thing. The average stress is small. And then uh, in the quench dynamics path, it doesn't, it is like the system is frustrated in a state. It cannot jump out of it because you are driving it at a very high loading rate. And so the average stress is very high. So these are the two extremes. Now, everything that is interesting lies between these two extremes. And of course, we are able to qualitatively explain this behavior of this. Okay, now that we have the equilibrium map, so at each lambda we have the kinetic transition network. These are some of the examples of the transition network. So as I already explained, the color coding, each ellipse is a stable state, and each black line is the pathway, the transition pathway or the minimal energy pathway that you can think of. And the red dot is a transition state. The color codings are energies. And again, this is a weighted graph in the sense that the edges and the nodes have several properties that are used in the statistical mechanics. And these are, I just want to show some examples of how this connectivity looks like. you can get such connectivity. These are all the equilibrium states, and you can see that all states. So this is the initial solution, and this is connected to all the defected states. So we can get all this, and it gets complicated and complicated. And this is by no means complete, and there is no way of assuring that it is complete. And one of the problems that I did not show you is that some of the configurations are entirely separated, because the bifurcation diagram is running this way and the PDKTN is this way. So if the bifurcation diagram turns and hits it at the other point, so this connectivity is missing. So although you see this is a connected set of solutions, there can be, from the same bifurcation diagram, you can see a disconnected set of solutions, because the bifurcation diagram is going here, coming here, and there is no connectivity between that. Now, what do we do with all this data, the potential energy surface that is evolving? So you use kinetic Monte Carlo, but here the loading rates are dependent on the loading parameter and indirectly time. So if time can parameterize lambda, and lambda enters into your system, and you can turn the crank to run lambda at different rates, that is lambda dot changes. So assume that you have a particular state. In regular kinetic Monte Carlo, you do not have this integral. You just have the transitions out of that particular state, and then you roll dice, and then you use first passage time based on the total transition out of this particular state and get the first passage time, and then you sample that using some distribution. And in the next stage, you select one of the states as an exit pathway by again sampling according to the weights of the outward transition probability. But here the transition probabilities are changing with time or through lambda indirectly. And so we assume we cut the bifurcation diagram at some discretization delta lambda. And so we can get all this data from the PDKTNs. So each slice, the information would be given by from a PDKTN. Then you can get the residence time in a particular well. Of course, that well itself is changing time. And then once you get the residence time, you can choose one of the exit pathways out of all the available pathways. And then you keep running this, and then you can construct a trajectory. You can run multiple trajectories to statistics evolution. But then our problems do not end here. Uh, One of the reasons why we choose kinetic Monte Carlo as opposed to molecular dynamics is that MD resolves. It's a Newtonian equation, and so it has to resolve the vibration at the vibrational time scale, sub of femtosecond time scale. So we want to leave that and accelerate our simulation. And so instead of doing MD, we have chosen a state-to-state dynamics using transition state theory. And so that saves us a lot of time. So instead of uh, spending lots of time inside a well where the intramodal vibrational energy redistribution eventually decides you to luckily kick out of that energy well, which is called a rare event. You leave that out and then directly deal with the transition between these two. But then there is one more thing in between these two is the low-lying energy barriers. When I say low-lying energy barriers, the barriers are large enough so that they are greater than KBT, and so the Markovian approximation is still valid and the transition state theory is good, but small enough so that the advantages that you get from kinetic Monte Carlo are now eroded, in the sense that the system flickers between a set of states without any progression in time. So your kinetic Monte Carlo algorithm keeps running lots and lots of iterations between a few set of states. If you want more information on this, you can look into works by Fichthorn from Penn State, or Brian Puchala and Krishna Garikpati from Michigan. They have done a very good amount of work on this. So what we want to do is essentially, if this is the transition network on a particular potential energy surface, on the fly, we want to identify the low-lying barriers and then treat them somehow and get out of that well without wasting too much of time flickering in within the well. So there are several ways to do this. One of the easiest ways, you just as you are going on the fly, depending on your graph, identify the transition, the states that are connected by low transitions. Any transition that is comparable to KBT, you just treat it as roughness because it should not be there in fact. Uh, and other ones which are like low-lying barriers, you group them into super basin. And the characteristic of the super basin is that the barriers inside are very small, but once it goes out, it is okay. So you can model the outer ones as absorbing states. So when you detect that flickering is happening in the system, you turn on your super basin algorithm automatically, and then it identifies the super basin, and then it manually integrates the master equation, and then finds the first passage time as well as samples exit pathway. That allows us to do a kinetic Monte Carlo on this evolving landscape. And now let us see the results of driven dynamics. So the the blue ones are at very low loading rate, and the red ones are at very high loading rate. And as you can see, the blue ones, the average stress is very small. Essentially, the system samples more region of that, and it can make transitions as the energy surface is evolving. But if you see the red ones, it is actually frozen in a particular, stuck in a particular state. And finally, these are some of the statistics of this equilibrium map. The edges, what all you people call equilibrium paths, there are around 200,000 equilibrium paths. So between two critical points. And out of these, 55,000 are stable, 75,000 are saddles, and higher order ones 64. And the nodes that those are critical points in the bifurcation diagram are around 200,000. So these are the points where implicit function theorem fails, and then you have the bifurcations, folds, all those. And then the bifurcation points are 10,000 and the rest are turning points. And totally, all the solution points put together are around 10 million points. And then the processing time is this. Of course, this was done before 2019, before me moving to Hong Kong. So we did not have enough computational time, but now I think we can do much better than that. We can do maybe orders of magnitude more than this work. And these are some data of manager and worker databases. Yeah. Finally, I would like to conclude. So we now have a systematic way. The completeness is a question, but at least to some extent, a systematic way of dealing with the non-uniqueness of the energy minimization. We now can deal with some kind of parameter-driven systems. And we have identified three regimes: the quasi-static, which is in the thermodynamic limit of infinite time, where the system can explore the entire energy landscape. And the other extreme is the quencher dynamics. The system can only roll down the hill. And in between, it is the driven dynamics. The system is driven at a particular loading rate, and this is where all the interesting things happen. And then on this evolving landscape, are able to deal with super basins. And everything is coded in MPI, a bit Fortran, a bit C++, in a very well functioning parallel code. But of course, there are some limitations that I'm aware of that I may address if I find time, but right now I'm not working on continuation anymore. Uh, the future extensions, if I have enough time, I would like to, I mean, this is not doable. But anyway, this is future extension, so I can say whatever I want. And then uh, there are some other interesting things that are happening, like on the potential energy surface when I'm doing steepest descent, there is something called a valley ridge inflection. So when you go from a transition state down to another transition state, sometimes this can bifurcate and there is a valley ridge inflection in there. I have seen several of them in the same diagram. My treatment during this PhD work, I don't think I have done a rigorous work of treating them. So if I had enough time, I would uh, treat these branch points very well. And then right now, the code that I have, I tested it until 1,000 cores because that is the limit on the Aerospace Engineering and Mechanics cluster at University of Minnesota. And it scales very well, so I did not see any overheads. The master node is perfectly doing well. And one of the things is that although I used the EAM potential here, I did not use lamps. I used Professor Tadmore's QE, that quasi-continuum QC, a quasi-continuum code in the fully refined state. Essentially, I'm not taking any advantages of a continuum region and an atomistic region. So that's a fully refined quasi-continuum. Our goal was to use to build in the framework so that in future we use this for multi-scale problems. But then I decided to graduate in between, and and so this is one of the future goals. And yeah, one of the questions the troubling questions that I always have this method is that I have shown a very impressive set of statistics. When people see, they think that, okay, you have explored so many paths, so many points, great. But then many of them on a potential energy surface are disconnected. So you have useful information, but then you have to throw it out. So there should be a more either maybe through deflation techniques or some other methods. You need to be able to at least in a particular region of the potential energy surface come up with a properly connected kinetic transition network. So that is one of the things that if I have time, I want to do this. So the way I thought is I have a bundle of solutions that are evolving, like the driven dynamic solutions. And then I do equilibrium, the path following on the fly. And then I explore within a confined region rather than a priori exhaustively computing the bifurcation path. I mean, I may be wrong, but that is one way that this can be thought. So essentially, on the fly, you locally explore and lift, locally explore and lift the PES through numerical continuation. The exploration is through KMC, and the lifting is through numerical continuation. So that's it.